So before the break, we started talking about circular motion. Okay? We said there's some new terms and values and things like that that we have to be aware of. Okay, like frequency, the number of times something goes around in a circle or makes an orbit, okay, in a certain time interval, okay, or period, how long it takes to make one complete orbit or cycle or circle. Okay, we talked about centripetal acceleration. Okay, and we used the term centripetal force. We haven't really gone into that much yet. Okay, so in order for something to go in this circular path, it always has to be what? Accelerating. Okay? It's always accelerating because its velocity is always changing. Any object going in a circle wants to go in a straight line according to Newton's first law. Some centripetal force, something, pulls it towards the center. That pulling force is constantly turning that object's vector. Okay, so when it starts out, the vector is pointing that way. But as it goes around the circle, the vector has to change so that it's always tangent, okay, to the circle. So as it goes around and around, you can see all of these vectors are pointing different directions because there's a centripetal acceleration that's changing the direction in which the object is traveling. Is it changing the object's speed? It is not. It's traveling at a constant speed, but not a constant velocity. All that's changing is the direction. That still requires a force, because any change in velocity is an acceleration. So even to turn something requires a force, according to Newton's second law. Okay, everybody all right with that idea? Okay, so for this example here that we see, this is the moon orbiting the Earth. What keeps the moon in orbit? Gravity, yeah. The Earth and the moon are gravitationally attracted to each other. Okay? We get this idea that it's all about the moon being attracted to the Earth because the Earth is bigger, but it's actually not the case. Okay? We'll look at this a little bit later on in the unit, but the Earth and the moon actually orbit a common center, and it's not the center of the Earth. Okay? It's actually a little ways below the Earth's crust, but not the center of the Earth. So the Earth actually wobbles back and forth as the moon goes around it, because it's trying to orbit the gravitational center of the system, which is not its center. We simplify it to make it look that way. Okay? So anyway, as the moon goes around, the moon wants to fly off in a straight line, but Earth's gravity, or the gravitational force between them, pulls it back towards the Earth, constantly changing its direction so that it orbits the Earth. It's not a perfect circle. Okay, it's slightly elliptical, and it's getting bigger all the time because it's also not a perfect system. Okay, and eventually the moon will fly off. Not tomorrow. Okay, your grandkids aren't going to have to worry about it. Okay, in fact, if we're still on this planet when it happens, we deserve what happens to us. Okay, because we should definitely have the ability to leave by then. Okay, so don't look up. I don't know if any of you have seen that movie. I watched it over the holiday. 2 hours of my life I'm not getting back. All right, so we got the moon going around and around. There's a net force and an acceleration always directed towards the center, and that's what keeps the object turning and going in that circle. Okay, that ringing a bell from before. So we looked at I watched the David and Goliath thing with you guys, right? Or was that my afternoon class? Okay, we're going to watch that here real quick. But the David and Goliath thing, using a sling. Okay, so in the Bible it says that David took 5 stones, I think it was, from the stream. Okay, and so what he did with those stones is he just made sure that they were, fairly uniformly shaped. Okay, kind of like a saucer. Okay? And put them in his pouch, and then took them into battle, basically. And all he had as a weapon was a sling, which is basically, it would have been about this big, okay, like completely unfurled. It would have been about this long, and it would have been made out of hemp. Okay, like that's what they would have made, those kind of fabrics. They would have braided hemp, okay, and made this sling, which would just be a strap with a pocket at one end. Okay, so where my thumb is would be where the pocket is. It would be slightly wider there. Okay. Then what he would do is he would put in that pocket, he would put the rock. Okay, and he would just kind of hang it at his side like this so that it wouldn't fall out. And then once you get it spinning, okay? Then you can go around and around like this. If it's going fast enough, it's not going to fall out, okay? But at some point, you're going to want to let it go, okay? Where do you want to let it go at? When its vector is pointed at your target. Okay, so he wants to let it go, okay, when it's spinning around and the vector is pointed here. Okay, now, that's no small feat. Okay, like the other day when I was demonstrating this to you and I let go of this thing right at the right time and it flew off and hit the board. Okay, I mean, it wasn't going very fast. Okay, and I made sure that it wasn't going very fast so I could accurately let it go and it wouldn't hit anybody. The opposite of what we wanted here, okay, or what David wanted here. So you'd have to really have a lot of experience with that. You'd have this thing whipping around and around and around, and then right at the right time, you let go of it. So in the sling, there's a part that's got a loop that goes around your finger, okay, and the other part has a knot at the end, okay. So you whirl it around and around and around, and when you're ready to launch the rock, you just let go of the knot, okay. When you let go of the knot, the strap or sling straightens, and there's no force holding the rock in the circle anymore, and the rock flies off in a straight line at a high rate of speed, okay, way faster than you could physically throw it, right, because you have the added advantage of extra length. There's kind of a lever, okay, kind of advantage there that multiplies your force, okay, and allows you to throw it faster, okay. Now, when you let go of that, you'll actually hear a snap or a crack, okay. Whenever, like, sometimes you'll hear it if you're just just whipping something back and forth. Like if you've ever used like an actual bull whip, okay? If you watch like Indiana Jones, right? When you whip that thing out, you heard it crack, okay? That crack is a sonic boom. Okay, the end of the sling breaks the sound barrier. That's how fast it's going. So more than 330 meters per second. That means the rock is going about that fast. Okay, not quite breaking the speed of sound, but okay, going very, very fast. Several hundred meters per second for sure. Right? That is not something you want to have hit you because it's going really fast. But that thing will snap, and at the end, it's a sonic boom. Okay? It's actually why the end gets frayed. Okay? Of a bullwhip or of a sling. The end with the knot will get frayed because every time it breaks the sound barrier, that's actually pretty hard on it. Okay? And it frays more at the end. Okay? Everyone kind of familiar with what I'm talking about? Okay. So I'm going to show you this video of David and Goliath, and then we'll, okay, now, you probably all have this, crazy friend who likes to drive really fast. Maybe you're that crazy friend, okay? But the radius of a corner makes a difference in how the occupants of the car experience the corner, okay? If I'm going around a 320 meter radius corner, which is still, mind you, a pretty big corner, okay, at 28 meters per second, which is pretty fast, it's like 100 kilometers an hour, okay? If I go around that corner, okay, that 320 meter corner, I'm going to experience a fairly large centripetal, or require a rather large centripetal acceleration, okay? Centripetal acceleration is v squared divided by r. Okay, it's the formula we talked about before the break. We actually don't use it all that often. Okay. So if I go around the corner at 28 meters per second and the radius is 320 meters, then this is going to be a pretty big number, right? 28 squared divided by 320 is going to give me a pretty big number. But if I do the same thing now on this much wider corner, so I'm still going 28 meters per second, but now r is 3 times bigger. So the corner's 3 times wider than this corner. My centripetal acceleration will be how much less? 3 times. 3 times less. Okay? Remember, the centripetal acceleration is v squared over r. V's not changing. I'm taking both corners at 28 meters per second. But the second corner is 3 times larger. So r is 3 times larger in that situation than this one. So the centripetal acceleration I would feel will be 3 times less. Right? This is why if you've ever watched racing or even in your own experience, taking a corner wider means you experience less of that being thrown into the door type of experience. Okay? Taking a corner wider or slower, okay, will reduce that sensation of being thrown against the door or out of the car or whatever, okay? Just by doing one of those two things. Which would have a bigger effect, slowing down or taking the corner wider? Slowing down, yeah. V is squared. So any change in V is going to have an exponential effect on A. Okay, so if I halved my speed, I'd have 4 times less, okay, of the acceleration. All right, so if we just look at that like very quickly mathematically, okay, for the first corner, for the 320, our centripetal acceleration is 2.5 meters per second squared. So that's about 1/3 of gravity. So if you were thrown into the door, the force of the door against your shoulder would be like 1/3 of your weight was piled on your shoulder. Okay, so it would be significant. Like, you know, that'd be one of those situations where you're plastered against the window, okay, and yeah, that'd be like that, right? But if we take the 960 meter corner, 3 times wider, the acceleration we experience is 0.82 meters per second squared, about 1/9, okay, of your like overall weight. That you wouldn't even be thrown to the side. You'd kind of feel that, you know, moving slightly that way, but you'd be able to correct your own posture in a situation like that. You wouldn't have to brace yourself or grab the holy crap bar, okay, you know, or whatever. Okay, you wouldn't need to do that. Okay, this is also a situation where you don't want to be in one of those Jeeps with no doors. Okay, I mean, you're wearing your seatbelt, obviously. Okay, so you're not going to fall out. But if you weren't wearing your seatbelt, what would happen to you? Out of the car in a straight line, just like the people on the merry-go-rounds we watched. You know, morons, motorcycles, and merry-go-rounds. The 3 M's of fun. Okay, so yeah, you would go out of the door of that Jeep. Okay, and if you were going around this corner, okay, and you went out the door of the Jeep, you'd go like this. Okay, in that straight line. Okay, that's why, well, among tons of other reasons, why you want to be wearing your seatbelt. Okay. Often what happens when people are killed in rollovers, okay, is because they usually roll on a corner, okay, and so they're turning this corner and the car begins to roll. They're not wearing their seatbelt and they get ejected from the car, okay, and typically when the car is doing this and rolling, you're typically ejected from the top. Okay? So, if you get ejected from the car, you will follow a projectile arc. What's going to slow down faster? You flying through the air or your car rolling along the ground? The car. Which means you'll land on the ground and the car will roll over. That's how people are killed when they're ejected from the car. Usually the car rolls over them. Okay? You gotta remember, you are part of that system. So when you're thrown, you are thrown in a straight line path from a thing that's doing the same thing you are. It's moving in exactly the same direction. Okay? But because it's bigger, heavier, there's more resistance to it, it slows down faster than you do flying through the air. Okay? And so when you land on the ground, the car is coming. So wear your seatbelt. You're always safer in the car than outside of it. Okay? There's always that rare 1 in a million case where someone gets thrown from the car and survive, and they're like, if they had been in the car, they'd be dead. Yep. Okay, but the 9,000 other times out of 9,001, the person would survive better in the car. All right. That making sense to everybody? Okay, just kind of the principles of circular motion. So we're going to skip that step. There you go. Okay. And we're going to go to centripetal force. Okay. So centripetal force is what causes the centripetal acceleration. It's the actual force that holds an object in a circle. And it's always directed where? Inwards, towards the center. Centripetal, remember, means center seeking. Okay, so it's pulling or pushing towards the center of the circle. Okay? And it can be a push or a pull. It depends what the situation is. Okay? Has anyone ever been inside a big tire and had people roll them? It's not common, but some people have done that. Okay? If you're rolling in that tire, can you stay stuck to it and not fall? You can. You just have to go really fast, okay? But you can totally stay pinned to that tire. It's the same as the gravitron that we were talking about, okay? The gravitron, if it went vertical, it went fast enough, you could be pinned to it, okay? So that you wouldn't fall out. The same is true on a roller coaster, okay? You do a vertical loop on a roller coaster, it's going fast enough that you won't fall out, okay? Yes, you've got the safety harnesses and everything, but you're not gonna fall out of that. You're gonna be pinned to the seat as you go through that loop, okay? And that's because of this centripetal force. So what keeps you in the loop is the seat. You push on the seat because of your inertia, and the seat pushes back towards the center, okay? And it keeps you in that loop. Okay, so circular motion cannot occur without a force that is pushing or pulling towards the center, okay? Lots of forces can act as centripetal forces, okay? And we're going to look at how those operate, and then we're going to look at unbanked curves, which are corners that are flat, and banked curves, so corners that are elevated, right? So exit ramps, like the one out here to get on Highway 2, that's a banked curve, okay? So that on-ramp that we take, okay, that goes around the corner and then gets on, okay, that's a banked curve. Right? Banked curves are designed to use centripetal force to make it safer to traverse the corner. Okay? Unbanked corners, they're not as safe, and their conditions can change drastically. Okay? So the speed at which you can take a corner here in town today could be different tomorrow. Right? If it was to like rain or get icy, okay, or whatever, the speed you could take those corners at changes from day to day. That big exit ramp out there, if you take it at 60, which is what the recommended speed for it is, it doesn't matter what the conditions are, you're safe. Okay? The conditions of the road for a bank curve are irrelevant to your safety to traverse it, provided you take it at the recommended speed. Okay? If you try to go faster than the recommended speed, then the maximum speed you could take it at changes with conditions. Okay? Everyone kind of with me on that? Okay, so Newton's second law tells us that F equals m times a. All right, we learned that in the last unit. This is still true for an object moving in a circle. Centripetal force, Fc, okay, is net force. If something's going to move in a circle, the net force has to be directed back towards the center. Okay, that's going to be mass times centripetal acceleration. Okay. Here's where the formula changes. Do we have, and we in fact just used, a formula for centripetal acceleration? Okay. Just a minute ago we said AC equals V squared over R. Okay, so that means this formula here is going to be written in this unit like that. mv squared over r is m times a for this unit. So centripetal force will be our net force. mv squared over r is m times a for an object moving in a circle. Okay, and the vector sum of all forces part still true. For an object to move in a circle, the vector sum of all the forces acting on it has to be directed towards the center. Okay, so we'll be looking at that as well. So all of those Newton's second law rules that we learned in Unit 2 still apply. They're just now circular. Okay, so in lots of cases, identifying a centripetal force is easy because the centripetal force is obvious. Okay? In this case, the only reason that the tape moves around and around in a circle is because of the what? What's holding it in the circle? The string. Yeah. Okay? If I let go of the string, the tension force that's keeping it in the circle is gone and it'll fly out. Okay? When we watch the moon going around the Earth, or the Earth going around the sun, there's no like material connecting the two. Okay? It's gravity instead. What keeps you in a corner, like an unbanked corner? So if I turn a corner here in town, what keeps me from going in a straight line? Friction. Friction can act as a centripetal force. It's less obvious because, again, we don't see something connecting the car to the center of the corner, unless it's the Batmobile. Okay? And it shoots out a cable and helps it corner faster. Okay? But we don't have that, and we just rely on friction instead. With a bank curve, we actually rely on the normal force. Okay, we push on the corner pushes back, and part of that's directed back towards the center of the circle. Okay, that's how a bank curve works, and we'll look at that here in a little bit. So one of the challenges in this unit is going to be to identify the centripetal force in a given problem. What's acting as our centripetal force? Right. Okay, so let's look at the effect of, first off, speed on centripetal force. So the formula says that centripetal force equals m times v squared over r. So just looking at that formula, what kind of relationship do speed and centripetal force have? Exponential. V is squared. Okay? So that means if I double the speed of an object moving in a circle, it will require 4 times as much centripetal force. Okay? So if I take a corner here in town at 20 kilometers an hour, I'll easily be able to turn that corner. If I turn that corner at 40 kilometers per hour, I'm going to require 4 times as much force to navigate that corner. Maybe the conditions are good and the asphalt and my tires can provide that extra 4 times friction to keep me in the corner. But I'm not going to know that until I suddenly don't have enough friction to stay in the corner. Okay? And that's when you slide out. That's what happens in the wintertime. Okay? You go around a corner, there's not enough friction, so you go in a straight line. Okay? I actually saw a guy last week who I thought for sure was going to hit us. That intersection out there by the new Chevy dealership that you go to get to Edison School there, okay? He came barreling down the southbound lane and into the left turn lane to go, like, turn to come here. And he was easily going 110 when he entered the left turn lane. And I'm looking at him and going, okay, so he's going to start that turn and he's going to lose it. Where is he going to be facing when he loses it? Is it going to be on a trajectory that's going to lead to me? Okay, so I was actually looking at, okay, I got to go this way. I've got to turn left as well to get out of the path of this vehicle. Okay, somehow he managed to keep control of it even though the back end of the truck swung out. Okay, and why does the back end of the truck and not the front end of the truck swing? Exactly, the back of the truck was lighter. So there was less friction pushing down on the back wheels, the motors over the front wheels. Okay, so the back end started to fishtail. Okay, he managed to keep it under control, but he almost went in the ditch. And why he had to be going so fast, I don't know. Okay, that's something you have to consider when you're rounding an unbanked corner. Okay, is that my speed is going to affect how well I negotiate this corner exponentially. Okay, so we're going to look at this one here. We're going to say the mass is 0.9 kilograms, and it's moving at a constant speed. We want to find the centripetal force, the tension in the string, for speeds of 19 and 38 meters per second with a 17-meter long string. Okay, so we'll go FC for 19 meters per second. Okay, so we'll have 0.9 kilograms times 19 squared divided by 17 meters. So 0.9 times 19 squared divided by 17. All right, so we get 19.11 newtons. Actually, we'll say 19.1 newtons. Okay, if I do that same calculation now and I'm going twice as fast, so 38. Okay, so we'll have 0.9 times 38 squared divided by 17 meters, okay? That FC is going to be how much bigger than that number? 4 times bigger. So 0.9 times 38 squared divided by 17. Yep. Exactly 4 times bigger. Okay, so 76.4. Okay. Now, what's the effect of mass going to be? If I double the mass, but keep the speed and the radius the same, how's that going to change the centripetal force? It'll double it. Yeah. Mass and centripetal force have a linear relationship, same as they had a linear relationship back in the last unit. Okay, if I double the mass, I need twice as much force. Okay. What about R? If I double R, what will happen to FC? It'll get cut in half, right? It's got an inverse relationship, okay, because we're dividing by, right? The only thing that's exponential is V, because it's the only thing with an exponent on it. Everything else will have either a directly proportional or inversely proportional effect on FC. Okay, so that's the calculation we just did, right? And then if we're looking at the effective radius on centripetal force, so keep the speed the same now, okay? And we use 11 and 22 meter long strings for this. We're gonna see that the 22 meter long string needs half as much force because it's twice as long. Okay, so the radius of 11, 64 newtons, the radius of 22, 32 newtons. Okay, we just plug in those numbers, right? We're obviously just dividing by a number that's twice as large, so yes, naturally, our answer should be coming out. All right. So, in an unbanked curve, okay, we're relying on static friction, not kinetic, okay, because static is bigger and better, okay, for traction. All right, so we rely on static frictional force to round a corner. If we're relying on kinetic friction, what are we doing on that corner? Skidding or drifting. Okay? If you drift a corner, you still go in a circle. Okay? But the drifting happens when you get the back end to swing out, and now your car is actually pointing at an angle towards the center, and the back wheels are spinning, and they're providing a force that is directed towards the center. Okay? So drifting a corner, while incredibly cool looking, is like the least efficient way to go around a corner. Okay? Instead of just letting static friction guide the car around the corner, okay, you're whipping the car around using Newton's first law to get the back end to swing out, and then pounding on the power to get the back wheels to spin and push towards the center. When friction would have done that all for you. Okay? But I know it's cool. You pull on the e-brake and back end flies out and power on and boom, thing goes around the corner. Okay? But it's also very hard to control. Anyone ever tried drifting? I'm not saying you should, ever. Okay? But it's not easy. Okay? Like the first time most people try drifting, all that happens is their car spins around like this. Okay? Because they just lose it right away. It's a very delicate balance to keep the car pointed, not quite on center, okay? And keep those back tires spinning, because if those back tires suddenly lock up and gain traction, you're in trouble. Because the car will want to try and flip, okay? Or the car will radically try to go towards the center of the circle, which is not what you want, okay? That's why most of the time when a car that's drifted a corner exits a corner, it fishtails a little bit, okay? That's correcting for that loss of traction, okay? You have to kind of let the car come back into pointing the right direction afterwards. Okay, we're not going to deal with drifting because it becomes a far more complex calculation. Okay, we're just going to do, I'm going around the corner like a sane person, okay, and relying on static friction to go around. Okay, so if I'm relying on static friction to go around a corner, my vector sum of all forces calculation looks like this. Would you agree? My centripetal force is being provided by friction. Okay, so no different than what we would have done in the last unit. Net force is the sum of all forces. This force is directed towards the center, and it's the only one. Okay, so then we would have mv squared over r equals mu times the normal force. And since this corner is unbanked, that means it's level, F normal is equal to force of gravity. So I can do this. Okay, which means I could solve for any one of those parts provided I was given the others. What number do I not need? Yeah, I don't need mass. Okay, because mass is on both sides, it becomes irrelevant. Okay, now, in the real world, that is so not the case. Okay, and it's not so much about the mass as it is about the mass's distribution. where is the mass located in a vehicle that's going around an unbanked corner. Okay? If you have if you have an unbanked corner like this, and you're driving a sports car, okay, you're driving, this box, really sporty looking box, okay, but it's very low to the ground, and most of your mass is concentrated right here, very low to the ground. Okay? If I'm taking that same corner in a cube van, okay, that's loaded, and I've got a lot of weight near the top, which is not how you load a cube van, by the way, okay? Center of mass could be quite a bit higher. What are you likely to do on that corner? Tip. Yeah. Okay. Anybody drive an SUV? Okay. In lots of light trucks, heavy duty trucks, and big SUVs, if you pull down the rearview mirror, or sorry, not the rearview mirror, the blinder, okay, your like sun blocker, on the back of there is a warning about taking corners at high speed and the fact that your SUV or truck has a high weight center of gravity, okay, and can easily roll, right? Because that's what can happen. You get going around a corner, and the inertia of this mass is to go in a straight line, but it's also way above the ground, so it wants to do this. You drive a sports car, yes, you still want to do that, but you're so much lower to the ground that there's less chance of tipping. You're more likely to slide out as opposed to roll over. Okay? A tall vehicle is way more likely to roll over in that situation than to slide. Okay? Making sense? Incidentally, if you're ever packing to move, the heavy stuff goes on the bottom for many reasons. It'll break all the light stuff if you put it on top of it. Okay? But also, it's much safer from a physics perspective to have the mass as low as possible. All right. So does this part here make sense? This sum of all forces? Okay. So this is the Skidpad test. Okay. The Skidpad test is run by all auto manufacturers. Okay. It's how they can rate the cornering ability of any given vehicle. Okay. Cornering ability is a statistic that lots of people want. Okay. Especially transportation safety boards and things like that. So what they do is they have a circle painted out on it's not a parking lot, it would be like a big parking lot. And they just paint this big circle. Okay? And they put a test driver in the car, and they say, drive around this circle, faster and faster and faster until you lose it, until you skid out or tip over. Okay? So the person just gets in the car and just drives faster and faster and faster until they skid out. Okay? At that point, they can figure out the cornering ability of the car. Okay? It's not based on speed. It's actually based on acceleration, on centripetal acceleration, because it's rated as a g-force, okay, or a factor of gravity. Most passenger vehicles are going to be able to corner somewhere around 0.7 Gs. That would be their maximum cornering ability. Okay? So that's your crazy friend taking the corner and throwing you into the window. Okay? Really high-end sports cars, very low to the ground, good tires, nice conditions, might be able to go slightly over 1 G. Okay? But you got to be well designed in order to have enough force that there's more force pulling you out of the circle, pulling you into the circle than is pulling you into the ground. Okay? That has got to be a very, very well designed suspension system, okay, in order to do that. All right. Okay, so let's compare the maximum speeds at which a car can safely negotiate an unbanked curve, one in dry weather and one in icy weather. So in icy weather, our coefficient of static friction is 1/9 what it is in the dry weather. Okay? How much slower are we going to have to go if we have 1/9 as much friction?
Third.
1/3. Right? The square root of 1/9 is 1/3. Okay, so you go 1/3 as fast if you have 1/9 as much friction. Okay, because remember, it's an exponential relationship. So let's have a look at what this looks like. So force centripetal is equal to the force of friction, and this is for dry. Okay, so we would have mv squared over r equals mu mg. Okay, we know already the m's cancel. They didn't even tell us the mass of the car. we're trying to solve for v. So what do I need to do with r? Multiply it over the other side. Okay, so v squared equals mu ger. Okay, I want to find v, not v squared, so okay, so the maximum cornering speed under these conditions will be v squared, or v equals the square root of mu ger. Okay, mu times g times r. Right, so for us, that'll be the square root of 0.9 times 9.81 times 50 meters. That's what the radius of the circle is. Okay, so square root of 0.9 times 9.81 times 50. All right, so we can take that corner under ideal conditions at 21 meters per second. That's not too bad. That's actually pretty fast. Okay. Under icy conditions, everything stays the same except mu. Right, so we're going to have mv squared over r equals mu mg. Okay, we're still going to have v equals the square root of mu g r. All that changes is mu now becomes 0.1. Okay, so inside the square root, we're going to have a number that's 1/9 what we had in the first calculation. But when we square root that, it'll end up being 1/3 the size. Okay, so that looks like 1/3 to me. Okay. So keep that in mind when it gets icy next winter, or this week. You know how weather in Alberta is. Okay. That you are going to require, it will be required of you to slow down, okay, by about 1/3, to about 1/3 of your other maximum velocity, okay, in order to successfully negotiate a corner. Okay, so unbanked curves are at the whim of road conditions. The speed at which I can take them changes depending on road conditions. That's not ideal, especially if we're talking about exiting off of, or more importantly, merging onto a high-speed road. Okay? The whole reason that interchanges have been built is to eliminate intersections, okay, where people have to stop and then speed up, okay? And there's a risk of, traffic intersecting each other and having accidents. So having an overpass and an interchange is safer. It's a lot more expensive. Okay, but it's also a lot safer. And it gives you a chance to merge in with traffic more efficiently, okay, than if I just turned right at an intersection and had to go from 0 to 110. Okay, that's why they're actually trying to eliminate all of those crossings like that on Highway 2. There's still a few here in town, right, where you can get to Highway 2, but it's an actual crossing intersection. That's not nearly as safe as using the overpass. Okay? And my ability to get up to speed there is a lot worse than my ability to get up to speed using a bank curve and an on-ramp. Okay? Because, again, I'm at the whim of the road conditions. Right? Under ideal conditions, yeah, put it to the floor and let the V8 do its work. But on the normal condition, under icy conditions, all that does is spin the tires, and then I got traffic barreling down on me at 100. Okay? And I'm still swinging around trying to get going at 30. Okay, that's not safe. Or you get stuck by that person who doesn't know how to merge and they're still going 60 when the lane runs out. You're like, oh my God, we're all going to die. Okay, a merging lane, by the way, is for accelerating. Yeah, don't waste time. Just, it's the pedal on the right makes it go. Push it down, okay, and you go faster. All right, so that's what we just did there. Okay, now we want to look at a bank curve. But you know what, let's take a little break here. Let's take a 4-minute break. Come back here and then we'll talk about how bank curves work. Okay, so the purpose of a bank curve is to eliminate reliance on friction. You don't have to eliminate the use of friction, okay, but you can eliminate it with a banked curve. Okay. How many people have ever been on a plane before? Okay, when a plane wants to turn, what does it do? It angles. Yeah, a plane is not like a car. Okay, it doesn't just turn like this in the sky. Okay, in order for a plane to turn, it banks its wings, right? Because just having a little rudder on the tail is fine for like minor course corrections. But if it wants to make a big turn, that's not going to be enough. And so what it does is it uses the only force that's not basically forward, okay, that it has in order to help it turn. And that's the lift that its wings produce. Okay? So by banking like this, okay, it's now taking the lift that its wings produce and angling it. So now they're not pushing straight up, their lifting force is pointed like this. So now there's not as much lift, but part of that lift, the horizontal component of it, is directed towards the center, causing the plane to turn. Okay? What does the plane do at the same time? It what? It drops. Okay? I mean, if you require this much lift, this total lift to stay level, right? As soon as you bank, part of that lift is now directed this way. So you don't have nearly as much force directed straight upwards as you had before. Okay? So a plane will start to descend. Fighter planes that are making tight loops fall while they turn, okay? Considerably, because they'll actually turn almost straight on their end. Okay? And so now their wings are producing only a turning force, and the plane is turning and literally dropping at the same time. Now, a passenger plane would not do that. Okay? They're going to descend slightly in a bank. Okay? When they're coming in to descend for landing, that's what they do. Okay? They'll often, I don't know if you've seen it here, but planes have their landing pattern that they use at the Calgary International Airport. Part of that landing pattern actually goes over Okotoks, and you'll often see planes that are circling. Okay? And they're circling because it's not their turn yet, but they're also trying to lose altitude before they come in to the runway. In very high traffic times, not all planes have the benefit of saying, hey, I'm a half an hour out, can I start descending now? And I'll just like come right on into that when I get there. No, you have to circle for a while until it's your turn to land. Okay? And so they'll, as they circle, they'll lose altitude, okay? And descend slowly.
Can they speed up?
Yes, but you're also generally trying to land, which means you have to slow down. If you wanted to maintain your altitude, yes, you would have to increase the engine's power, okay? Get the air to fly over the wings faster, creating more lift, okay? Then this line gets longer, this line gets longer, the lift part, right? And so does the cornering part, okay? The problem with that is you don't want to make the ride uncomfortable for the passengers, because the faster you turn, the more G-forces are produced, right? So when you've got a pilot who's making those kind of turns, that's when they can black out. If they do it at a high rate of speed, their blood will want to leave their brain, like that video, the guy who passed out, okay? Same thing, that's what can happen. You don't want that with a plane full of passengers. They paid good money to not black out. That'll make the oxygen mask fly out, and then there's panic. People won't like that, probably.
So when you are using the rudder, are you changing the direction of the plane?
Yes.
And then do you turn because of the engines going forward or no?
You turn for the same reason a boat turns when you use the rudder. So you're trying to go through the water, and if you've got the rudder straight, the water just goes by the rudder. Okay? But if I turn the rudder slightly, the water on this side of the rudder is slowed down and pushes on the rudder, which causes the front end of the boat to go the other way.
Okay.
Right? So same thing with a plane. If the rudder turns like this, the plane turns that way. Right? Because this end of the plane slows down. Yeah.
But the angle of the plane changes, the velocity doesn't change immediately, right?
Well, no, the velocity changes, the speed doesn't change
Okay.
right away. Yeah. Right? Because it's a circle. Right? We're just moving through a circle. We don't want the speed to change. We just want the direction to change. Yeah. So we're assuming we're keeping this thing's speed the same.
Okay.
But as soon as we eliminate some of the lift, the plane will start to descend. I'm not saying a passenger plane is going to do this and fall out of the sky. Okay? They're not obviously going to slow down that much or bank that much, but a fighter plane, it will. Right? But they go really, really fast. Okay, the same is true for banked curves that we would drive on. Okay? On a bank curve that we would drive on, we're not reliant necessarily on friction. Sure, I can go out here to this 60-kilometer corner and take it at 80. I'm not saying you should, okay? But I'll admit to having done that, okay? And as long as the road conditions are okay, I can still do that successfully. There's some friction there that can keep me in that corner beyond the 60. Would I choose to do that on a day when that's covered in ice? No, I'm smarter than that, okay? On that day, I was 60. And exactly 60. Not faster and not slower. Because if I go slower, I won't slide out of the corner. I'll slide into it. Okay? That's the delicate balance of a banked curve. Okay? So what you're doing with a banked curve is this. It's another inclined plane. See, they're so useful. Okay? So a banked curve is an inclined plane that's a corner. Right? So if I'm just sitting on the corner like this, obviously I don't slide down into it. Agreed? If it was frictionless, would I slide into it? If I just park my car there and this thing is frictionless, it's going to slide down into the middle. Okay? So if I'm going around this bank curve and it's frictionless, but I'm actually moving, okay, I can make it so that if I go the right speed, I can still negotiate that corner, even though there's no friction between my tires and the road, simply by harnessing the nature of a bank curve. Okay? Obviously, there would be a force of gravity. And when we're just talking about a bank curve, that's the biggest side, or sorry, when we're talking about an inclined plane, that's the biggest part of the triangle. When we're talking about a bank curve, we're adding normal force. We're making the normal force bigger. So in a normal inclined plane, normal force is this side of the triangle, and it's smaller, and this side is F parallel. Okay? When we're dealing with a banked curve, we're changing that. And what we actually do is we make normal force the biggest part of the triangle. How do we do that? What about going around a corner as opposed to sliding down a ramp changes the normal force?
Driving into it, same question.
Exactly. When I go around a corner, I still want to go in a straight line. And as a result, I push on the corner. And the corner pushes back. Okay? Now, it pushes straight out. But there's a horizontal component of that that's directed towards the middle. Okay? Everybody kind of with me there? Right? And then there'd be gravity that would be this side of the triangle. Right? So, actually I'm going to draw it the other way just so that it's on the top. So we would have this, okay, force of gravity, and we'd have this, okay? This will actually be our centripetal force. Because as I go around the corner, that vector is always going to be pointed towards the middle. Okay? Now, how do I calculate the force of gravity? What's the formula? M times G, right? Okay, what's the formula for centripetal force? mv squared over r. Too close. mv squared over r. Okay? That's that side. This angle here and that angle there are equal. Okay. So my centripetal force is the opposite side according to this, right? Normal force is my hypotenuse and centripetal force is the opposite side. Okay? So if I knew the normal force, okay, I could say that centripetal force equals the sine of theta times normal force. Everybody okay with that? Okay. I'm just going to put the formula in for that. Okay. Force of gravity is the adjacent side. Are you okay with that? Okay, so centripetal force is the opposite side. Gravity is the adjacent side. Okay? What an urban planner or a highway designer wants to do is calculate the angle of bank for a bank corner. They already know how much room they have, so they know what R is. Okay? They probably already have a safe traversing speed in mind. It's usually 40 to 60 kilometers per hour, somewhere in there. Okay, so they'll already have that in mind. All they need to do is calculate what angle do I need to bank this corner at so that people can take it at that speed regardless of what the weather is like. Okay? So what they do is they say this angle is based on this side divided by this side, right? Opposite over adjacent would give me this angle. Okay, so opposite over adjacent is tan of theta. That's going to be mv squared over r divided by m times g. What happens to the m's? They cancel. And what I get left with is this. What does that mean for mass? For an unbanked, for a bank corner? It doesn't matter. I mean, have you ever taken an exit ramp where there was a whole bunch of speed signs? If you're this heavy, go this fast. If you're this heavy, go this fast. No, we don't want, that's ridiculous. Why would we do something that would require every single different mass of car to go a different speed? We don't want that. We want every car that goes around that corner to be able to take it at that particular safe speed. Okay, so we just go v squared over r times g, and that could give us our angle of bank. And they would know how high they need to bank the corner, okay, and it'd be safe to go. Now, as I was saying at the start of this, a bank corner can be negotiated at whatever that speed is, regardless of whether there's any friction or not. But you have to be careful. If there's no friction, if it's really, really slippery, don't go slower. It can be just as dangerous as going too fast. If you go too fast, you'll slide into the guardrail on the outside. If you go too slow, slide into the middle. Okay? Either way, you're off the road. So, I've actually seen this happen. Back before they did the whole Stony interchange at McLeod there on the south end of Calgary, there used to be, I think it's actually still there, that little bit of road that would get you from 22X onto McLeod Trail northbound. Okay, so there was a bank curve for that. And one day I was doing it, I was going in, and it had just done a bunch of freezing rain. It was covered in what was like almost frictionless ice. Okay, so I'm coming into that corner, driving cautiously. I see that the speed limit is 40. And I'm dead on 40 as I start to turn. The guy in front of me panicked, and he hit the brakes, which did very little because it was so slippery. Okay, but I saw the brake lights come on, and he slowed, just ever so slightly. And I'm like, oh crap. Because I knew exactly what was going to happen to him. He was going to slide in. Okay, like there's that delicate balance. I didn't want to go any faster or change my radius because that could change which speed I would be going at. If I tried to avoid him, okay, if I went in or out, that would change the speed at which I could go, and then I would risk sliding in. If I tried to avoid him going out, I could slide in. If I tried to avoid him by going in, which would be crazy because that's the way he was going to go, I could slide out because I changed my radius. So I had to just like trust physics and just stay in that lane and stay at 40, knowing that I would be okay as long as I went at the speed that was built for that corner. Okay? And he slid right into the middle because once he started sliding, there was nothing he could do to stop it. Okay, because he hit the brakes and then realized, oh no, as he started to slide in, then I could see the tires start to spin. Well, that lot of good that's going to do, you're already sliding. Okay, hitting the power now, your tires are just going to spin as you slide into the middle. So It's one of those things where, yeah, sure, under ideal conditions where I have friction acting as an additional force down, would have a component towards the middle, I could take that corner faster. Okay? We never deal with that because it brings in a lot of extra calculations, but in the real world, that's how a real banked curve works. Yeah, there is some friction there. Very rarely is it ever frictionless. This is why they bank racetracks. And if you've ever watched NASCAR, right, it's just like a big oval. I don't get what people find so exciting about cars just driving around in a constant circle, but whatever. Okay, they just go around and around, and the corners are banked. Now, they're not banked like our corners. Exit ramps on normal roads are less than 10 degrees. Okay, they're a very shallow bank. All done? They're a very shallow angle of bank. NASCAR corners are very, very steep. So steep, in fact, that when they put the paving machine on them to fix the roads, so they're banked like this. That might be a bit of an exaggeration, but they're so banked that they actually have to put a crane out here that holds the paving machine on. It actually has to pull this way to pull the paving machine onto the corner, because the paving machines will either roll or slide down the corners because they're going very, very slow. Okay? Those corners are designed for cars that are going very, very fast. And sometimes they even go too fast and they lose it and go into the wall, right? Okay? But a car that has a tire blowout or the engine fails, where do they always go? Down into the middle, okay? Right away. Having that steep angle ensures that any car that's velocity changes goes either out or in, okay, and out of the way. Well, into the wall is generally bad because they tend to bounce off the wall and hit other cars. But if they fail, they slow down and go into the middle quickly. All right? Making sense? All right. So this is what I crudely drew. I forgot I had this picture. Okay, so we got force of gravity acting down, okay, and then we've got, you know, this force acting up that's going to counteract it, and then we've got our centripetal force here, okay, and then we could calculate that angle. That's what we were looking at before. Okay, and this is the derivation that we just did. You will never be required to derive this, okay, to derive the formula here, this formula, okay, that's on your formula sheet. Okay. I just showed you how we derived it so you understood kind of where it came from and what forces contribute to it, but you will always have the banked curve formula. Okay, so this is the banked curve formula. Now, for all curves, the same things affect them, right? If we're looking at an unbanked curve, which we looked at just a little bit ago, okay, where we said mv squared over r equals mu times m times g. Okay, if I solve for mu and I divide these things over, the m's cancel, divide both sides by g. It's v squared over r times g, right? Regardless of which corner you are dealing with, okay, the things that affect either coefficient of friction or angle of bank are speed, radius, and gravity.
So does that mean the coefficient of friction and the angle are the same?
They're not the same because they're not the same kind of corner. This is a corner that's banked like this, that you go around it like an exit ramp coming onto Highway 2, okay? And this is an unbanked corner, right? So friction holds you in this one, angle of bank holds you in this one. Okay, so that's kind of what we were looking at before. Okay, and we did say that yes, there is a force of friction. We indicated that it's here and it acts down the ramp, but it would then also have a component of it, a horizontal component that points back towards the middle and also acts to aid as a centripetal force. Okay, because remember, centripetal force is still the vector sum of all forces. So we would have our Fc from the normal force plus our Fc from the force of friction. Okay, both of those would contribute in a real world situation. Okay, so if we wanted to determine the angle at which a frictionless curve should be banked for a speed of 35 meters per second and a radius of 550, we would just manipulate, or we wouldn't have to do much manipulation, but we would just solve for theta. We have V, we have R, we know it's on Earth, okay, so we can calculate that. To get theta would just be inverse tan of 35 over 550 times 9.81, okay, and we would get that it's banked at 13 degrees. That's a pretty steep corner, okay? 13 degrees doesn't seem like a lot, but it is, okay? We kind of get this idea of, you know, hills being steep. On a road, if a hill is more than, I think it's 6%, there has to be a sign saying that this hill is steep, and it's often rated as a percent of grade, okay? What that means is how much of your what percentage of your upwards compared to your across, okay? A really steep hill could be 9%, okay? So that means you're going, for every 100 meters forward, you're going 9 meters up. Okay, that doesn't seem like mathematically, when you think about it in your head, that doesn't seem very steep. But if you were going up that hill on a bike, it would be really steep. Okay, so when we bank a curve, we don't make it really, really steep because it's way easier than to slide into the middle. Okay, if you've ever watched any of that indoor biking in the Olympics, okay, the same thing. Like those curves are wicked. They're wicked steep. Okay, and if they fall, they slide into the middle right away. It's not practical to make curves we would use every day to be really steep. Okay, it's just, I mean, would you have to worry, like, let's say I've got coffee in my cup holder, and for some reason I don't have a lid on it. If I go around that corner, will it spill? Nope. It's going to be pinned to the bottom of the cup, just like I'm pinned to my seat. Okay, if the coffee spilled, then I should fall into the passenger seat by the same logic. Okay? But I'm pushed into the seat pushes on me, the coffee's pushed into the bottom of the cup pushes back, shouldn't spill. Okay? If I'm going the correct bank, if I'm going the correct speed for that angle of bank. If I go any faster than that, coffee spills. Go any slower than that, coffee won't spill. Okay? Not that you would ever drive around with an open, uncovered cup of coffee or anything else in your car, that would be crazy. Okay, I'm gonna do that one. I don't wanna do that one. Okay, this is a good one to talk about. So I'm gonna have you guys write this one down, okay, and give it a try. See if you can get this one solved. Okay, and then we'll talk about it. This one has to do with this. Have formula from the first day of this unit. Alright, so for this one here, we were given the period. We were told it takes 0.4 seconds for the tire to make one complete revolution. Okay, the radius of the tire is 0.36 meters. Okay, and we're looking for the speed of the pebble that's stuck in the tread, okay, at any one time. So V equals 2 pi r over t. So we'd have 2 times pi times 0.36 divided by 0.4. All right, so the rock is moving at 5.7 meters per second at any given time. Okay, how does a rock stay in the tread of a tire? What keeps it there? Friction. Okay, think about it. You jam something in between the treads of a tire. What keeps it in there is the fact that the treads of the tire are squeezing it in there, and there's friction, so it won't fly out until you're behind that car. Okay, because that's Murphy's law as applied to new windshields. Okay, the likelihood of getting a rock in the windshield is inversely proportional to the age of the windshield. The newer the windshield, the higher the chance of getting a rock in it. It's totally true. Okay, totally true. You get a brand new windshield, I guarantee you, you're going to get a rock in it in the next 3 days. Okay, all right, especially if it's winter time. So, why does that happen? Like, rocks always come out of a tire at the same place. Where? Where do they come out of the tire? Like, at what point in this circle is the rock going to come out? Here? If it goes here, then when it comes out of the tire, it goes up and hits the wheel well. Saves my windshield. Yep, right here. This is where they come out. Okay? And there's a couple of reasons for that. This is a vertical circle, so there's a bit of gravity here. The rock's velocity is actually changing a little bit in this thing, and it's fastest at the bottom. Sort of true. Okay? But the other part of it is when your tire hits the ground, it changes shape. Right? It's a little flatter on the bottom, and that spreads out the treads. So just as your tread is coming off of here, it's open a little bit more than it is up here, which means it's more likely for the rock to come out. And what makes the rock come out is when its inertia is greater than the friction that's holding it there. Okay? Which means it's when the person in front of you is doing what? Traveling at a constant velocity, speeding up, or slowing down? Speeding up. Because as they speed up, the speed of the pebble increases. And with greater speed, greater friction will be required to keep it there. Eventually, there'll come a point where the friction in the tread is not enough to hold the rock there, and the rock will fly out directly into your waiting windshield. Okay? So when the person in front of you is accelerating, back off. That is when the rocks come out. If they're at a constant speed on the highway, they're far less likely to come out. They still could, based on the nature of the road and things like that, but they're most likely to come out when the person is accelerating, because the force that's keeping them there may not be strong enough to keep them there as the speed increases. Okay? So once that thing comes out, okay, it flies up as a projectile and comes back down. If you are in that path, you are getting it in the windshield. Okay? That's what will happen. That's why lots of big trucks have what on the back? Mud flaps. Okay? The mud flaps hang lower down, so hopefully they catch most of the rocks as they are ejected from the wheels. Okay? So if the car in front of you has mud flaps, you're good. Unless those mud flaps have been on there for a very long time and have gotten shorter and shorter, and who knows that happens too. Okay? But there's a real life application physics for you. Okay? If the person in front of you is accelerating, they're far more likely to throw rocks at you, okay, than if they're traveling at a constant speed. So you should stay a bit behind them in those conditions. Okay? It's usually why when someone passes you and they pull in, right, they're accelerating past you. That's when the rock flies out. Okay? So if someone's going to pass you, back off. Okay? That's when you're likely to get it. All right, let's call it there. We did a lot today. And tomorrow, we're going to do a lab on the effect of radius and speed. We're going to whirl things around in circles. And I'm going to test your hand-eye coordination. Big time. Fun for me.